The broadcast is now starting. All attendees are in listen-only mode.
Hi, everyone. I am Mark Olson, and thanks for hanging on and waiting. We had a few presentation issues here, and I'm going to end up driving the slides on my end for this presentation. So I'm going to be limited on what I can see, but I do want to kind of introduce this. This is the week's 3-4 S2S webinar series that it's co-sponsored between the NOAA Weather Program Office and the NWSSTI. And we have monthly seminars. Today, we only have one seminar, and that is Zhaoxia Pugh, and she's going to be talking about strongly coupled land-atmosphere data assimilation and its influence on near-surface weather forecasting. If please ask any questions in the Google document, it should be linked in the chat there. And so we'll be able to take questions when she's done. There should be plenty of time for questions. So I'll go ahead and turn it over to Zhaoxia, and thank you very much for speaking today.
Okay, thank you for the introduction. Good afternoon, everyone. Yeah, I'm very glad to have this opportunity to talk to this group. So I know this is the week 3-4 and the S2S group. I was asked to give this talk, and I was wondering if it fit this group or not. But in fact, what I told is land atmospheric data assimilation are very interesting in this group, and so I think I'm not directly address any of these 3 to 4 weeks or S2S prediction, but emphasize on land atmospheric data assimilation. So this coupled data assimilation may be useful for some of you, and hopefully which will need more discussion in this topic. So yeah, before the talk, I would like to first acknowledge my former and current students and postdoc who work on the coupled land atmospheric data assimilation with me, include Dr. Liu Fanning, Junkai Liu, and also Qing Huang is current student. I also would like to acknowledge NCEP EMC for the collaboration, and also NOAA JTTA and NGGPS program for support this research I presented here. So in this next slide, please. So in this talk, I'm going to give some background information and also mainly talk about the some of the work we have done to understanding the covariances between the land surface and atmospheric states. Because in order to do the coupling, we need first to understand the correlations between the land surface and atmospheric states. And also in the early study, we have done some work to compare the strongly and weakly coupled land atmospheric data assimilation, and the results showing the strongly coupled land atmospheric data assimilation overperforming the weakly coupled data assimilation. We have made some efforts developing strongly coupled land atmospheric data assimilation with NCEP GSA based ensemble common field data assimilation. And recently, we moved to developing the strongly coupled land atmospheric data assimilation with UFS and JEDA. So we will just showing some preliminary results on this development. And also, finally, I will make some concluding remarks. Okay, next, please. Okay, so just to give a background, so the land atmosphere interaction in the numerical weather and climate prediction are the essential component. So we see the coupled land atmospheric data, coupled land atmospheric model for both weather and climate prediction. So mainly we have the land surface parameterization. So previously in the model, so nowadays we have land surface model with very more complicated components. So we build up the land model. So now mainly the error for the model come from both atmospheric model and the land model in terms of land-atmosphere interaction. And we also see the bias of the prediction all the time. Most of studies showing the soil moisture data simulation can have positive impact on the weather and climate forecast. So the soil moisture data simulation seems to be concerned recently. So land, in terms of the general question, so the land state, the soil state, like soil temperature, soil moisture, are the concern for the data simulation. So next, please. So most notably, land atmosphere coupling is essential in the near surface and the boundary layer. So we see the because of the atmosphere directly interact with land, and so near surface weather forecasting and the atmosphere boundary layer condition are mostly influenced by the land condition with the time evolution. So this type of the influence can also influence upper atmosphere and also stay for the longer time period and the influence to weather and the climate prediction. So next slides. So in terms of the NWP concern, so with our early NGGPS support the research, so we have evaluated the near surface weather forecasting, and we see the large error in the near surface weather forecasting. So here the left panel showing you the mean bias and the rolling square error for the 2-meter temperature and the 10-meter wind from the NCEP global forecast system. And we compared this US mountainous region in the west and the plain region in the east side of the country. You can see the both in terms of the bias for the 2-meter temperature. So you can see it's pretty notable in both east and the west side of the country, but we see large error, especially in the mountainous region. And in terms of the wind, so it seems like the wind error relatively smaller than what we see from the temperature, but still you see the large biases, and especially in this west side of the country, so the diurnal variation was shrunken by this near surface forecast error. And notably in this, based on the case study, we also see in the errors for the some case we can accurately predict the phenomena, for instance, front system and also the atmosphere inversion. But even though we predict the phenomena, but near surface error, like the near surface temperature error, sometimes can be like the 10 degrees Celsius. It's pretty much very large. And so the increased model resolution sometimes could help, but it still cannot reduce bias in the near surface weather forecasting. So therefore, so this is very a critical question, and also it cannot be just addressed by atmosphere model alone, and we need to think about the land surface effect. Next slide, please. So this motivates us to look the land atmosphere interaction and to see how much we can see the soil moisture on influence on the near surface temperature. So for instance, here, so with the previous student, so we published a paper in the JGR, which address our observational study. So we did find this 16 soil moisture station in a different land use and land cover. So fortunately, so yeah, they are very representative, and so we find the co-located soil moisture station and along with the meteorological station. And also there are 2 sounding stations among these 16 states, so we can study the from the observation what's the correlation between the soil moisture and surface 2-meter temperature, and also what's the correlation between the lower atmosphere temperature and upper atmosphere through the sounding. So what we basically get the conclusion is there is an interaction between near surface variable. So with so please come back to the previous slides. Okay, so yeah, we actually find that so there is a correlation between the soil moisture and the surface 2-meter temperature. So as you can see, the correlation among these 16 stations are less than 0.6. So even there are correlation and there are kind of like notable, but the direct correlation are not very strong. So this is just the mean value over the season, over the different months. So we see the warm season, we can see high correlation than the cold season. There is also an interaction between topsoil layer and atmosphere. So impact of soil moisture on the near surface temperature are certainly significant. So which means even a correlation number is 0.6, but in many locations, topsoil particularly have the significant correlation with near surface temperature. And in terms of the surface and upper atmospheric correlation, so this has a strong flow dependent on the weather condition, and also some of the seasonal variability. So as I said, the warm season, we see the strong mixing, so then the correlation will be strong, and the cold season will be staying in the lower level. And also it depends on the land use and the land cover. So we did this observational study, so then we see the correlation, and then so we also did the sensitivity study with the model. So next, please. So we used the single column model, which is one of the options for the Wolf model, and we did perturb this soil moisture based on the climatology variability in a year, and so we performed the sensitivity for the different seasons. So as you can see here, so this is surface near 2-meter temperature responded to the soil moisture change. So you can see there are the change of the soil moisture in the different seasons certainly have the different magnitude of the response. So in the warm season, we see more significant response. So the change of the soil moisture will certainly cause a change of the near surface temperature. So this is proved. So there is a strong coupling between the soil moisture and the near surface temperature. So if you compare this soil moisture perturbation influence to the wind, you can see these influence are much smaller than we see in our temperature. Okay, so next, please. Okay, so then because of these correlations, so this motivate us to do the more deep study with to understand that within the data assimilation system. So what is the correlation between the soil moisture and the near surface atmospheric condition? So now basically, so we did build this B matrix. So with this is variational data assimilation. So it is use the optimization method. So which means we build this cost function measures the distance between observation and the background field, and also observation. And so the analysis and the background field and the analysis and observational field. So this B is the matrix represents the covariances between the observation and the background. So usually how we sorting this is, so we try to find the optimal analysis which best consistent with the background and also close to the observation. So this background error covariances determines how much modification we will make from the analysis for the to generate analysis from the background. So then so this is very important metrics to have. So we did actually use the multiple year and then months data and that to build up these correlations and then find out so what's the characteristic of the in terms of the covariances between soil moisture and the near surface temperature. So as you can see here, so we see that this is all time and the daytime and the night time. So you can see from the temperature and the moisture and also UV1 component, you can see actually we see the large correlation between the soil moisture and the temperature and the near surface temperature and near surface moisture. So in terms of the vertical structure, you can see consistently for the even for the different year. So the boundary all normal portion of atmosphere are strongly influenced by the soil moisture. So which means there is strong correlation between this soil moisture and the normal part of the atmosphere. So the correlation with the wind is relatively weak, but with respect to the temperature and the moisture are very significant. Okay, so next, please. So this gives us also the confidence we can. So there is a strongly coupling between the soil moisture and the near surface weather forecasting conditions. So then we just want to test so whether strongly coupled data simulation would do better job than the commonly weakly coupled data simulation. So here the strongly coupled data simulation meaning so assimilation of soil moisture will feed back to the atmosphere variable, or assimilate the atmosphere variable will feed back to the soil moisture, which means soil moisture assimilation will adjust atmosphere variable, or the atmosphere variable data assimilation will just cause adjust of the soil moisture state. So that is strongly coupled data assimilation. So the weakly coupled data assimilation usually is we do the atmosphere data simulation and then land surface data simulation separately, and then couple them together when we start to run in the model and forward with the integration. So a lot of the common methodology is weakly coupled. So this is we do the strongly coupled data simulation. So we use the SMAP data and emphasize on the US continental domain, and our verification emphasize on this Southern Great Plain region, which was identified have the much more stronger non-atmospheric interaction, and also we have the in situ network to do the soil moisture network to do the verification. So before doing the data simulation, so this is satellite data, so we needed to do the bias correction. So in fact, so this is what the model CDF of the soil moisture, and then so this is what SMAP data, and then so after the CDF matching bias correction, you can see the we can correct the CDF for the observation and the model closely. So this is a necessary step for the satellite derived soil moisture data simulation. Okay, next, please. So basically, we running the made the evaluation to compare the performance of strongly coupled data simulation and the weakly coupled data simulation for the influence to the near surface weather forecasting and also the precipitation forecast. So to keep the story short here, so we consider this strongly coupled data simulation definitely outperforms the weakly coupled in terms of the near surface temperature forecaster biases and the rooming square. So compare with this meta weather station data. And also for the precipitation, we also get a slight improvement. So it's all positive impact. So which means the strongly coupled DA, which simulates the soil moisture data, has an impact on the near surface variable, and which lead to the better near surface weather forecasting. Okay, next, please. And then the next thing is because of this early experiment, so we want to use GSA ensemble common filter system to develop strongly coupled land-atmosphere data simulation. So we did this with two steps. So first step is to add soil moisture as a analysis variable in a GSA data simulation system. And then we simultaneously assimilate this near surface 2-meter temperature, 2-meter wind, and also this soil moisture. So altogether, so simultaneously assimilate this data, and so then through the cross covariances, the soil moisture data simulation can adjust the atmospheric data, and the atmospheric data simulation can adjust the soil moisture. So we did it for the 1 month data simulation experiments. We choose July, which is a warm season, and we done a series of the numerical experiments, and so we simulate this US Southern Great Plains region soil moisture network in situ data to test the idea. Next, please. So as you can see, we did the verification with the soil moisture, and also the near surface 2-meter temperature and the humidity against the observation. So I mean, because this paper already published in Monthly Weather Review year 2020, so you can check the details. So the story here is assimilation of soil moisture improves the near surface atmosphere prediction, and in the meantime, so the assimilation of this atmosphere seems like also improves the soil moisture condition. So which means that both soil moisture and the near surface atmosphere and the humidity condition was improved by the simultaneously assimilate this soil moisture and the near surface atmosphere variables. So I mean, this is with the GSA, we get this get this practice of this strongly coupled DA, and so it seems like there is benefit to the near surface weather forecasting. And then with most recent requirement from the NOAA, so we begin our new project to move to the UFS and the JEDA. Okay, next, please. Because we were told we must use the UFS and the JEDA because those are the current operation system. If we want to do any type of the new developer transition, we have to use this. So then here we start to work with UFS and the JEDA, and so we worked on this, how we perturb this UFS and also soil state, and so build an ensemble and use LETKF data simulation method and to conduct soil moisture data simulation. So next, please. before we start, we also did the seminar investigation and to see the correlation between soil moisture and so near surface temperature in UFS. So here is the correlation. So for the different levels, so in terms of the soil moisture correlation to the atmospheric temperature. So as you can see again, so this is very similar to the what we seen from the previous wolf model study with GSI, and so this strong, we see also the strong correlation in the lower part of the atmosphere, mostly in the boundary layer, and also in laser spatial variability. So this is the lowest model level, the correlation between the soil moisture and the near surface temperature. You can still see in many of regions we can see the strong correlations. So which means it is possible we can still use a strongly coupled data assimilation to use soil moisture to getting improved near surface temperature analysis and forecast. So next, please. So here is another example. So which also showing a consistent conclusion. So even this is in our Africa region. Okay, so next, please. So then we move to the soil moisture data assimilation, and the first thing is we also look the soil moisture bias and the SMAP data compared with this UFS soil moisture state. So we actually tested this so CDF, the distribution of the soil moisture in the analysis cycle, also compared with different forecast time. In the short range forecast, we see very consistent distribution from the model. And then you can see, so there is only very slight differences between the different leading time, but definitely all of these are different from the SMAP data distribution. So I already mentioned that this CDF match is one of the methodology to do the soil moisture bias correction. So we did test the CDF matching method to do the bias correction. So here you can see this orange line is which is after the bias correction. So because for this case we have small sample of the data, so we did not get the exact match, but we still work on this, use a large sample. But since the methodology still works, the CDF matching can be a methodology which we can do the bias correction with soil moisture data. Okay, next please. So as far as the recent progress, we did actually have the soil moisture data assimilated into the JEDA for the land part, and also tested the soil moisture data assimilation on the mid-range weather forecasting. So far what we see is there is only slight improve of the surface temperature forecast from soil moisture data assimilation. So we also did include in the verification package to see the soil moisture verification and also the forecast. And so you can so there is only slight improvement because of the coverage of the single satellite data. That's one of the reasons. And also move to the atmosphere, whole atmosphere forecast. So next, please. So we basically seen the okay, please move previous one. Okay, so we basically seen the neutral impact to the upper atmosphere from soil moisture data assimilation. So at least as far as now, in terms of the assimilate soil moisture into the JEDA with LETKF, we feel these results give us some confidence because at least we did not hurt anything, and so the soil moisture seems data assimilation seems work. So we are now move on to the build the strongly coupled data assimilation. So I think that we are still have some additional development needs to be done, and also a lot of tests needs to deal with this cross covariances and also localization and all of these things. And so this is now we just working in progress, and hopefully can just report in the future. Okay, next please. Okay, so just to finish up with a couple of concluding remarks. So first, there are correlations between soil and atmospheric states. A strong coupled land atmospheric data assimilation is recommended. So because we early study seeing this strong coupled DA could be better than this weakly coupled DA. And also, so we practice this strongly coupled the DA with GSI in TF, so which demonstrate potential benefits in predicting near surface atmospheric condition and the soil moisture. So I also showing some of the progress with UFS JEDA. We are still working on this. And in the meantime, definitely after we have this strongly coupled data assimilation build up, we hope to evaluate the influence of this strongly coupled land atmospheric data assimilation on mid-range weather forecasting. And also, we will also move to test the influence on the 3 to 4 weeks and also S2S. Yeah, the reason of this is not only because this 3 to 4 week forecast extension of the mid-range, but also because of the this near surface atmospheric condition are certainly very important for the 3 to 4 week weather forecasting or S2S, because I think the near surface forecast error are one of the main source for this extended period of the forecast. We're looking forward to the move to this direction in the future, and hopefully get some input from this community. Okay, so this is all I have. I think I have next slides. Just next, please. Yeah, thank you. Just thank you for your attending. And so yeah, let me know or write me email if you have any question. Thank you.
Great, thank you very much. Looking in the discussion document, I'm not seeing any questions. If anybody has any questions, go ahead and put them in the discussion document and we can get them asked here. I did have one quick question for you, maybe for anybody else. The correlations that you show between soil moisture and, for instance, temperature and humidity, is there a latitude dependence at all on that? Do you know? You know, especially, especially between like the tropics and the tropics and.
Yeah, that's very good question. I think in the contour plot you actually can see. So mostly, so what we found is these correlations related to land use and then land cover. So I mean, in the it's actually also depend on the soil type. But I think in the region which was noted by previous study, like I think there are some people in the NASA Goddard that they did, and I have a science paper which actually note some of the region around the world has stronger land atmosphere interaction than others. So what we found is this type of the correlation are associated with this. So in the region which has identified as a strong land and atmospheric interaction, definitely so the soil moisture and the near surface atmospheric temperature and moisture will have more correlation or high correlation in this region. So in this strongly, so it's indication of the interaction, non-atmospheric interaction.
Great, thank you.
Yeah, I think it's more depend on the land use, land cover than the latitude.
Okay, great. We do have
Thank you.
questions I see so far here. Let's see. How does the 2-meter temperature bias change in the 5-day forecast using SCDA, strongly coupled DA, I assume, as compared to the control?
Oh, so how does, I think the, yeah, just move, maybe move back the slides a little bit.
Okay, let me. And how far back here?
Yeah, further back. And then, yeah, okay, continue back. Yeah, okay, here. Next, please.
Forward. Okay, that one.
Yeah.
Okay.
I think in the paper we published in the 2019, which actually have exact number. So, but here for this plot in the left, so you can see the this weekly for the temperature bias. So with weekly coupled DA versus the control, so without the soil moisture data simulation. So the average is 4.8, and then so the with strongly it's 7. So it's kind of like yeah, you can calculate the percentile there, but there are some like 15% or something. So if you look the beneath of this RMSE, so it's about 15% improvement.
Okay, great, thank you. Any other questions? I am not seeing any. If anybody has any further questions, they can actually at any time go into this document and type in questions, and we can, especially if you alert us to it, if you think of a question like tomorrow or something, and we can pass the question along. So we will go ahead and end there for today. And I would like to thank Dr. Ko for excellent presentation. Really enjoyed that. Thank you very much. And to everyone else, I hope we will see you next month. We're still working on trying to finalize some speakers. There will be an email sent out on that when we do. So thank you. And thanks again to our speaker.
Okay, thank you. Thank you for everyone for your attendance. Thank you.